Keith is muted.
Yeah.
Sorry, there we go. Thank you. So welcome to this webinar. My name is Keith. Thank you, Laura, for introducing me. I specialize in CFD at Qfinsoft at the Irene office. So I'm going to get started with the HVAC design and simulation webinar presentation, and then after I'll give a couple of demos. Okay, so hopefully you can all see my screen. So heating, ventilation and air conditioning, HVAC, basically forms a very important part in building services and engineering projects. Not only does it effective HVAC systems implications for energy usage, they also directly affect the experience and in many cases the health and safety of people. So the design requirements generally, when you're dealing with some HVAC problems, you would need to design and size of equipment. You would need to generally manage air quality and the distribution in buildings, and you would also manage thermal comfort. So those are the main things when we're dealing with HVAC problems. So how do we do it? So there's a few options that I'm going to talk about. So the first one that we do quite a lot of is ventilation. And ventilation is forming a lot of big part of designs of buildings. So the main customer goals is to meet air quality specifications and get even distribution throughout the building or the room that you're analyzing. You also want to look at removing of emissions, any noxious gases or NOx or SOx. And then obviously you want to be able to size equipment for specific rooms and see if your equipment will handle the different loadings that occur in those layouts. And then obviously you want to determine equipment layout, for example, in data centers and things like that. Or where you want to place diffusers and outlets and things like that. So what challenges we generally have is these enclosures are unique. So we can use basic principles, but to get a very good feeling of what's going on, CFD can be a very good tool. And then proof of concept, a lot of design, a lot of tenders now require CFD to prove that these layouts and the equipment is all spec correctly. And then obviously the challenges is to size equipment correctly and then analyzing various scenarios that may be present in these situations. So what capabilities does Fluent have or Ansys have? So we can do transients and steady state analysis, things like local mean age we can analyze, which is quite important when you're doing HVAC ventilation. Then you can do multi-species, and multi-species being able to handle different types of gases, noxious gases, for example, and then particulate flow as well, if needs be, if there is any dust or anything that you want to monitor. And then you could also do smoke tracking using the multi-species or the particulate method. And then the solutions, Fluent has a very accurate flow solver using all various, being able to handle multi-species and all that. And then you can custom script different fields like logarithmic mean age, which is not directly built in, but it's quite easy to implement, which I'll show a bit later. And then when you're using things like Workbench, you'll be able to do design exploration and be able to look at a whole different variety of scenarios. Or you can manually do that, but you can do design exploration on different scenarios. So what kind of inputs can you get? So the main things is flow visualizations of like flow fields, like contours of velocities and pressures, and also path lines and vectors and things like that. Quantitative reports and qualitative reporting can also be done. And then the benefits of this is obviously proof of concept before commissioning, and adhering to like green building standards and understanding the flow characteristics and under all different various conditions. And you can see the effects of different things. And then you can each size get a good idea of the size of equipment that you are requiring. That brings us to the next thing, is thermal comfort. So thermal comfort also comes into ventilation a lot as well, but ventilation more dealing with forced and natural ventilation, where now thermal comfort you're bringing into temperature and energy as well. So the importance of, or the goal would be to maintain temperature to a satisfactory level under different scenarios, and make sure that there is an even distribution of temperature. You don't have hot spots or anything like that. And then you can size equipment very much like ventilation, where you might be sizing fans in this, where here you could be defining cooling units or crack units or something like that. Then the engineering challenges, once again, the enclosures are unique and have various different layouts. Then you want to get the right equipment and ensure that all the equipment manages under different scenarios. And then you can look at the various scenarios and heat loads and even solar loading and things like that. So those can all play an impact on your design. So the capabilities, again, we have steady state and transient, but added to the fold now would be the energy solving, which introduces things like buoyancy forces due to the change in density. Then you can also look at the heat sources and solar loading, and then all the different heat transfer modes, conduction, convection, radiation, and a combination thereof. And then you can look at the effects of relative humidity and things like that as well with the comfort. And then very important, you can do semi-transparent media, things like glass, so which allow more heat in than that does out. And it's then the solution. So added to that would be the energy solver, as previously stated, the flow solver, and you can also do custom scripts and to extract various information, or you can create custom field functions that you want to use. Then that allows you to do various design explorations and analyze various different scenarios. Okay, the outputs, you can get flow and temperature fields, quantitative and qualitative reports for different fields like velocity, pressure, temperature, humidity, and things like also heat fluxes. And then you can also look at thermal comfort based on activity levels and on clothing and things like that. And then the benefits, obviously you understand the flow and the thermal characteristics of the room or the enclosure that you're analyzing. You can size equipment before commissioning, and you can also use analysis to improve design, which then will ultimately reduce energy consumption, which is a very important thing. So that brings us to another important topic that seems to be quite present in modern day HVAC stuff, is particularly in the CFD, and that's the requirements to do data center analysis, and that is a requirement for tender purposes and processes and everything. So the customer goals is to check if the cooling equipment is adequate, and also to ensure there's evenly flow and prevent short circuiting, and to prevent any hot spots, to ensure that there's even flow, and that then allows reduces any hot areas. And then you understand the effects of failure scenarios. If a cracked unit goes, how will the data center behave, or the flow behave in the data center. And then you can determine equipment layouts, optimal layouts, and things like that. Yeah, and then the engineering challenges. So thermal management for multiple scenarios is important, and obviously sizing of equipment, ensuring those are the correct meet spec, and then finding optimal layouts. And ensuring those failure modes also work well. So the capabilities that we offered would be a steady state and transient if needed. You can have energy with heat sources. You can add buoyancy forces. Then you can use porous media, and a good way to model your racks would be to use porous media and couple that to some form of fan, and you can use fan modeling, and that would be a surface that has a pressure rise across it based on the flow rate. And then you would be able to model vents, grates, and louvers as porous jumps, as also 2D surfaces, which have a pressure drop across it based on a flow. And then the solutions, very accurate flow, and energy solvers. Again, you can use custom scripting and then design exploration to look at different scenarios, failure scenarios, different heat loads, and things like that. So the outputs would be flows and temperature fields, path lines and vectors, and quantitative reports. All those would be of temperatures and velocities mainly of the importance, and you would want to see if there are any dead spots or hot spots throughout the data center. The benefit is you understand the flow and thermal characteristics throughout the data center. You have a very good understanding of what's going on. You can size equipment before commissioning, and you can understand different failure scenarios, and you can reduce energy consumption if you're sizing your equipment correctly for the loads that are occurring, and you can optimize your flow conditions. Okay, so then the next thing is equipment design. So the first few were more on a larger scale, looking more of enclosures and rooms and buildings, where we can also look at equipment design with tools like Fluent. So the goals obviously for equipment design would be to reduce the time to market and improve the efficiency and the design, and reducing the cost doing so. And then meeting specifications to have something to show that there is proof that it works. And so the engineering challenges that we would have would creating a competitive design, which nowadays requires some form of optimization, and to reduce development costs, because CFD is significantly cheaper than doing prototyping, which in the long run is a better option, and it's generally a quicker option. And then you can create, obviously you want energy efficient units or designs, and you want them to meet specifications. So the capabilities that Fluent or CFX or other tools like that have would be steady state and transient, coupled with energy and heat sources. You can do compressible flow and incompressible flow, and then multi-species and multi-phase, because you may be looking at multi-phase in an evaporator or something like that. So you can have multi-phase, and then moving reference frames or moving meshes for things like pumps and fans and things like that. And then under the solutions, accurate flow and energy solver and the custom scripting. And then the most important thing added to the design exploration, you can also do optimization where you can get surface responses and be able to optimize your design based on those. So the outputs would be flow fields, temperature fields, pressure fields, but these are really depend on the design that you're looking at. It could be volume fraction of a various fluid. So it does depend on the design. But the important thing, you would be able to get some surface response, which you would be able to then use to optimize your design if you use a design space or design grid to create a response surface. And then the benefits would be to reduce the time to market and reduce the development cost while doing so. And then improve the overall design, making it more efficient, which ultimately is something we all want to achieve. Then the last thing I just want to highlight on, which something that can also be done, which has an effect on HVAC, and that's external flow of buildings. And that could also be external loads like solar radiation and things like that. So the customer goals would be the environmental effects of the buildings and the structures, and ensure building meets safety regulations, and then understand the effects on HVAC equipment. So all your auxiliaries and that can have an effect, be affected by external flows and things like that. So the engineering challenges we have with such conditions is wind loading. Does that affect the building structure? Does it have vortex shedding due to that wind loading? Then also solar loading, and then again you can have opaque, semi-transparent media where you can allow heat into the building as well. And then obviously the effects of the surroundings and pedestrians is important, and looking at air pollution and how that can affect surroundings. So the capabilities, we can do steady state and transient and energy and heat sources, compressible fluids, wind profiles, buoyancy forces, solar loading, and multi-species. So we can do all of those above. So it does depend on what you want to use, of what physics you want to be using, but the capabilities are very advanced and broad. So the solution is an accurate flow and energy solver, custom scripting, and design exploration. So the external flow, the outputs, we can have flow visualization, temperature fields, frequencies from vortex shedding, things like that. We can visualize plumes of pollution, and we can also look at other quantitative and qualitative reports, pressures and things like that, or mass fraction or volume fractions. And then the benefits is obviously we can reduce environmental effects and reduce effects on surrounding buildings and surrounding environments. And then we can also adhere to building codes if necessary. Okay, so that brings me to the end of my presentation. I'm going to go on to showing you a demo. I'm going to do two demos. The first one is with Discovery, something which is the entry level CFD for Ansys. It's very quick answers. It uses GPU solving, so you get your answers very quickly. So for early stages of a design, it's a very good tool to use. So this is Discovery. So I'm going to just close this. I'm going to browse to a folder. I'm going to import a space claim file. Okay, so I just have a bit of ducting, and inside that ducting, let me show you. I can change the display of this. Let's change it to transparent. And inside you can see there's just a butterfly valve type thing. And I'm going to just simulate the flow through this, and I want to see how I can get balanced flow with this specific layout. So the first thing I'm just going to do is going to create a reference for this butterfly valve. I'm going to select that. I'm going to move that, and I'm going to add a parameter. Right, and then I'm going to set it up so I can go to preparation. I need a fluid volume, so I'm going to do a volume extract. I'm going to select all my inlets for the volume extract. So there are my 3 inlets. You must ensure it is closed off, and then I select a seed face, any face, internal face, and I'll create a volume there. You can see the fluid volume that is created. The next thing is I need to create boundary conditions, and I'll go to my simulation for that. Then I can go to my fluid flow, and I can select flow. Then default is inlet. I can select that inlet, and I can specify 1. I can type a unit in, but by 1 meters per second, I can select enter. And then it will add it to my list here of boundary conditions. Then I want to add outlets here, so I'm going to specify outlet, and 0 gauge pressure is fine. I'm going to select, and I'm going to repeat that for that outlet as well, 0 gauge. Then I want to change my liquid. I can double click that. There's a number of different in the database I can use depending on licenses that you have available. So I'm going to change that to air, because we are dealing with HVAC, which is mainly the case. So that is done. Then I can go back to my flow conditions. Then I am actually finished. I can click solve with my boundary conditions. Oh yeah, there was something I wanted to add. I want to add custom monitors, and I want to add volume flow rates at my various outlets. So I want to add one there, and I want to add one over there to see the balance of my flow. Yep, so you can see already I've got an answer, and we can see that it's not very balanced at all. So I can then manipulate that angle. So I can select that angle and change that to, like, let's say 10 degrees, and update that, and it will update the flow conditions quickly, and we'll see it get results quite quickly on seeing how that will affect the flow. Okay, so there we go. So the second one, the volume flow rate is a bit better. So now let's go to, we can do design exploration, and we can add chart, and we can add various angles to that at, let's say, 30 degrees, and then we can select all of them, and I can select solve. Let's say 22.5. Let's add one. So 40. Okay, and then we can solve them all, and we can then see how that affects the flow. Okay, so I'll allow that to solve for a little bit. So it's fairly quick, uses the GPU solver. There is the option to further this if needed, to go to refine mode. In the refine mode, it uses a, in the refine mode, it uses a tetrahedral mesh, and uses a built-in Fluent solver. And then you can take that further and go take it to Fluent itself if necessary. So we can see how that has changed. So at 22 degrees, this has come down a bit and this has come up. In absolute values, obviously the negative being outlets. And we can see how this affects the flow, and 45 degrees is a very steep one. So that might mean that I might overshoot a little bit. Again, then we can visualize that as in a graph as well. Right, so there we can see, so 45 is too high. We want more to closer being, I think 1 and 1. So we're looking at more of a somewhere around 20 something degrees instead. So yeah, that's discovery. So quick ways of getting answers, and you can change designs and quickly see the answers. So it's a very good tool for early stages of your design, especially conceptual designs. And then, as I said, you can go to the refine mode where you can further use the Fluent solver, not the GPU solver. And then you can take that to Fluent itself, where you can use it depending on your license, the flagship Fluent. Okay, the next thing I'm going to show you is a Fluent demo and a little bit of an HVAC thing. So this is my geometry. So I have a little bit of a room. I have an inlet diffuser here. I have an outlet vent here. I have a person sitting next to a table, next to a computer and a computer screen. And then I have this unit that can sanitize air, so we can look at the various scenarios on that. Okay, so now I'm going to take this to Fluent. So I'm going to go to Fluent Watertight Geometry. I'm going to put it onto 3 for now, and I'm going to select Start. Okay, just one thing I want to note is this is one fluid, one volume, but I have added name selections to all my things. So there's my inlet diffuser, there's an outlet grill, there's all my main walls, there's my ceiling, my floor, my table. I've highlighted all the surfaces, the intake of the unit, the outtake of the unit walls, the computer walls, and then the screen, as well as lastly the person. So I've selected the surfaces of all these objects, all these items, and I've created name selections on them to make it easier when you move into Fluent. Okay, so then Fluent is open. I'm going to just open a workflow. So I'm going to open a workflow that I created before. Let me just show you it. Okay, so I'm just importing the geometry. So there's my geometry. I can hide that if I want to. And then I can see inside. Then I just want to add some local sizing. So I'm adding just on the diffusers and the inlets to make sure that it's accurate there at that point. Sorry, my screen is doing funny things. Okay, and then I'm going to update that. Then my surface mesh, this is my global settings. So I'm in minimum size of 5 mils, maximum size of 50, and then a curvature angle of 18 degrees, and split any edges into 3 cells minimum. So then I'll create my grid. Okay, so it's created it. Then I must describe my geometry. So it's both fluid and solid regions, or voids. So I do have voids inside here. So you can see the surface mesh it's created with a finer mesh in those regions. And then I can describe my geometry. I don't need to extract any fluids because I've already got that. I've just got the fluid regions, and I can just then I can update my boundaries. So all my inlets and my outlets are just going to describe as velocities for now, and my outlets as pressure outlets. And then all my walls are just defined as walls. So then I can update my boundaries. And then I can create the region. Okay, so I need to define which region is dead, and this fluid is my main fluid. This one is a dead region. I don't need it, so I'm just define it as dead and update that. Then boundary layers, I can add a boundary layer on different walls if necessary. I'm just going to add a general, let's say, of 7 throughout on all the walls. And then I can create my volume mesh. I use generally polyhex core because it creates a nice polyhedral mesh on the surfaces and a nice hex core mesh. And a hex core is generally the most accurate, depending on the flow, but generally the most accurate cell that CFD cell that you can use. And then we can generate the volume mesh, which might take a little bit of a moment. It won't take too long. And we can see what. Oh, that's not working. Okay, we are nearly there. Okay, once we've created the mesh, we would move over to Fluent itself, the solution mode, and we can then set up our problem.
I see there's a question.
Okay, so this is very nearly done. So there we go, it's completed. So we can see what our mesh looks like throughout our geometry. So we can see our mesh. By mistake, reset that. Okay, so you can see the mesh through different things, and you can see in the inflation rate. Right, if you want to, we can see the quality is not great. It's not terrible, but it's not great, and we can improve that using the improve by right-clicking on generate volume mesh and adding improve stage, and then you can improve the. Most likely it will succeed, but it does depend on what you're trying to. I'm trying to get 0.2. 0.2 is generally best. So, or anything above 0.15 is good. And this is 0.2, so I'm happy. So I can save this and go to Fluent solution mode. Okay, so there we go, it's opened. So firstly is we're going to define, we can see our fluid, and that is air. Okay, and then we want to define our operating conditions. So we're going to define gravity, and gravity is minus 9.81, and we're going to specify operating density, and we can have that as accept that. Okay, then we can then we need to define our diffusers. So we can specify a velocity or a mass flow. So I'm going to actually change that type to an inlet mass flow. And then I'm going to define it as a swirling diffuser. So I'm going to add 0.2 kilograms per second, and I'm going to add changes to local, and I'm going to change that to 0. Again, or changes to expression and have that as cos 28 degrees. Sorry, that should be in brackets. And this one I want also as a function, and that's going to be cos of 90 degrees minus 28 degrees. Okay, so this has just helped me apply a swirl component to my outlets. Then I keep the rest. Obviously, I want it on my y-axis, and I need to specify an origin of 0.95, 2.9, and minus 0.5. So that's the center of my unit. Then I can apply that. Then my discharge, I can also specify a flow rate. So I'm also going to specify a mass flow rate. So I'm going to type inlet, and I'm going to specify also 0.2. And then I want to apply it at a direction of like in my X and Y, so 45 degrees outlet. Okay, then my outlets, my grill, I want it as a pressure, but I want a target mass flow. Sorry. I want a target mass flow. Why is it doing this? Can't. There we go. Okay, and a target mass flow of 0.2, and the pressures I'm happy with. And then I can specify that. And then my intake for my outlet, this I can also change to a mass flow outlet. And it's 0.2. Okay, one thing I did then specify is my energy, my diffusers. I'm going to just have as, okay, let's change the temperature if I wanted to. Go to units, go to my temperature unit, change it to Celsius. Then I can go to my diffuser unit, change it to, let's say, 15 degrees Celsius. And then I can change my unit discharge. I can define that as a goal. So I'm going to add a named expression, and I'm just going to call that unit temp. And there I want a or a reduction of mass flow average of my static temperature. And then I must define my location, and I can use a location, and that would be the outlet air intake. Okay, going to apply that, and then I can use that as for my inlet temperature here. I can have that as my unit 10 and apply that. All right. Then other things that I can do is use a UDF. So the UDF that I'm going to show you is for logarithmic mean age. And this is a simple UDF. This is all it is. We can share it with anyone who needs it. And you're just going to go to your user defined. We're going to go to compiled. We're going to add that UDF, and we're going to build it. It will take a moment to build, and then we can load it, and it is done. Then we can add scalars. I'm going to add 2 scalars, both of them for mass flow rate, and then in the unit, I can add a source term, and I can add that for and use the UDF local mean age source, and I'm going to apply that for both of them. I've added 2, and I'll explain now where 2 come from, and then I'm going to apply that. Then I'll just need to define the boundary conditions for that as well, so the UDS. So we're going to define a value at my diffusers, and at the diffusers it's fresh air, it's clean air, so it's 0, 0 for both of them. Then for my inlet, for my discharge, or for my unit, I'm going to, for the first one, I'm going to specify the values, second one as well. This one I'll use an expression. Let me add a definition, surface report, let's say area weighted value. And that will be of the second of the first one, and it's going to be at the unit intake. Yeah, I don't need any of that. I'll just apply that, and then I can have an expression where I use a report definition as my appliers. All right, and then that's basically it. Then I would add a number of different report definitions, but let me show you the solution. So I have already a solved one with everything in. So this is the temperatures. So you can see the temperatures around everything is a bit hotter. This is at 30 degrees. Sorry, what I did do was I added on the walls, on the person, I added a thermal as fixed temperature of 36 degrees. the screen, I added a power, and that was the wattage divided by the area of the screen. So it gave the heat flux. So I used the heat flux there, but I used a function of the watts divided the area, and I repeated that for the computer. So then I can get my different temperatures. I can then also look at things like my velocities. So if I edit that, I can look at my velocities throughout. Okay, so you can see where the higher velocities are coming out of the diffuser and out of the unit. And then an interesting thing would be to show you that this is fresh air. So it comes in the diffuser at 0, and then you can see where it is hotter, where there's areas where, so on this side of the room, it's fresher air than on this side of the room. So there's definitely a bias on this. And then the next one would be the clean air. And I'm going to show that the difference is the unit sterilizes the air. So this is then cleaned. So then you can see where the cleaned air is. So a little bit better, but majority, there's still definitely a bias. Yeah, so I hope you enjoyed that presentation and the demos. And yeah, if you, I think we have any questions, we continue from there.
Thanks a lot for that, Keith. I think it was very good. And as you could see, there's so many questions during the session, and Feinand and Stefan has been answering some of them, but we still have time to answer some questions. Erin, I don't know if your question has been answered. Alternatively, if there's any questions that hasn't been answered, you're welcome to ask now. You can unmute yourself and you can just ask the question unless you want to put it in the chat. See if there's anything.
I have answered the next one.
Yeah, you answered that one. Vainant answered.
Lara, a question from my side. It's Carl here.
Yes. Hello, Carl. How are you?
Yeah, thanks. Thanks for this great presentation, Keith. A question from my side. I'm actually a SolidWorks Flow, have a SolidWorks Flow simulation background, but recently moving towards the Ansys world, which is still very musty for myself. So the question is how to approach Ansys South Africa for extra courses, whether structurally or this CFD, HVAC, etc. Is this there? Do I have to apply through you, Lara, or through Dani, or how do I want to go about it? Where can I see some courses, maybe annual courses, etc.?
Yes, so you can contact myself or Dani. There's courses on the Ansys Learning Hub. So if your company have access to the Ansys Learning Hub, you can get access via that. Alternatively, we can share training courses and material with you, or we can schedule custom training for you yourself. So luckily, we've got a very wide spectrum of options depending on what works for the client or the company. So Carl, in your case, I would say just send the email to myself and Dani, and then we will follow up and give you some recommendations.
Great stuff. Thanks, Lara.
Pleasure. I think that was the last questions. Oh, new message, or is that thank you? No, there's more questions. There's one from George and one from Mustafa. So there's one. Yeah, I just want to say.
Stefan here. I'll just quickly answer the questions verbally. It's maybe just easier. So in terms of Discovery not being compatible with AMD, as AMD and NVIDIA uses different mathematical codes for the equation that they're solving. And Ansys made the choice to go with NVIDIA instead of AMD, and that's why only the NVIDIA cards are compatible with GPU solving for the Ansys products. So that's the one. The other one, the size problem solved by Fluent. So Fluent is the flagship CFD code from Ansys. So that, I mean, you can do millions of cells, hundreds of millions to be honest, and do any type of CFD, you know, solving that you would like. So large complex models, full buildings. There's virtually no limit if you have a big enough computer to solve all of that. It can be done.
Hello, I'm Mustafa here. Do you hear me?
Yes, Mustafa, I hear you.
So I am asking this question about the size of Fluent Solver. I know it can handle a lot of
yes,
number of grids and so, but I am comparing it with other softwares that are used in similar HVAC problems. So I had a debate or a discussion 2 days ago with one of the companies that Solver Fluent is very sophisticated tool for designing, but not for applying. Not as easy to use Fluent for application. For example, if you have a contract to estimate one building, to estimate the heat capacity and to specify the equipment for that building. So is it easy to run Fluent in this case?
Yes. Well, I'm not sure to which software you compare it to, but obviously, as you mentioned, Fluent is a general code. It's not only for HVAC. So obviously, it has a lot of functionality that maybe for HVAC you won't necessarily use, which is fine. But I mean, it's not difficult to set up. As Keith now showed, that's basically okay. That was now a small, you know, just a small room. But that same application can be applied to a large building with multiple rooms, multiple levels, and so on. And the complexity is not much different to what he showed already. It's just adding more boundary conditions, more source terms, and so on. So in terms of that, it's not, the complexity is the same as what he showed, basically. We've recently done several simulations of data centers, you know, where still in the design phase, where they want to determine whether the cooling equipment for those data halls is adequate and what will happen if some of the units fail. So those type of things can easily be done with the Fluent software.
Thank you.
If you don't mind, I just also have just some input on that. Maybe from my side, I'm Mustafa, it's Wynand here. So something to keep in mind is any software that you know well will obviously be easy to use, right? So the first time you use Ansys Fluent, you might need to learn a couple of things. But as soon as you get used to the software, setting up HVAC problems is really, as Stefan just mentioned, it's really not that complicated. So to give you some idea of in the past where a lot of the work went into when you were doing HVAC applications was actually generating the mesh and slicing up your geometry to get a nice hex mesh. But with the polyhex core technology that Ansys now has, that Keith also showed, it's really a very automatic process to get a mesh that can give you very good results. So with all of these new methods and technologies, you will just need to spend a bit of time with the software to get used to the interface, as with any software, but actually setting up an HVAC problem and getting good results is really relatively easy. And if you've set up the problem well, it can be quite fast as well.
Thank you. I'm very thankful to Qfinsoft, the company, for arranging this workshop and webinars. Thank you very much.
Oh, sorry, Keith. Don't you want to maybe just show quickly, if your Fluent is still open, how to create a pipeline?
I think it is open. Well, let me share my screen. Sorry. Right, so under the solutions, you would just be able to go to, or under results, should I say, and you would add path lines. And I could, for example, add a diffuser. I can have a cylindrical. I can have it based on velocity. And then let's just skip a couple paths just to be careful. And then I can click to see what that looks like.
Just maybe add the geometry.
Yeah. Oh, there we go. Yeah, so I very easily add path lines and particle tracking and things like that if necessary. Are there any other questions?
Hello.
Yes, hello.
I'm Elfas Matare. I am just trying to find out the affordability of the Fluent software. If you just give me the price, the minimum price that someone would need to procure the software. I'm sorry, I came a bit late. Unless if this information has been provided, I apologize. And then the other thing is, what are the minimum HPC, the computer capabilities that can actually effectively run a Fluent software?
Hi, Elifas. So I think just to answer your question on the price, it's very difficult to just say a price offhand because there's different pricing schedules for academic and industrial uses and so forth. So for that, I would recommend sending us a mail with your details, and then we can communicate about that directly with you, find out exactly your need and what you need to do, and what software or what package would be most suitable, and then we can communicate the price on that. So I'd recommend just sending an email through to us on that. But based on what you need for your computer, I think Stefan can also correct me if I'm wrong, but it's also quite dependent on what you'll be solving. But what we've generally found to be sufficient for problems is a CPU in the range of an i7 or an i9 CPU, and you're looking at 32 to 64 gigs of RAM about. So that's if you're solving, let's call it general problems. So if you're solving very large problems, you might need to use several computers chained together. But that is for very large problems. And again, that will be very dependent on what you need to solve. So if you do send through that email communication, I think we can take it a bit further and discuss what you would need given the types of problems that you would solve. So I'll just write, I'm going to give you I think you can send a mail to myself and Laura, and we will then communicate to you further based on your needs, what the pricing and requirements would be. So I'll type both email addresses into the chat at the now, and you can just send a mail to us and we'll communicate further if that's okay with you.
Okay, that's fine. Thanks.
Okay, so that's mine, and I'm sending Laura's as well. Just send the mail to both of us and we'll take it further. Okay. George, sorry, I see you also asked about the price. Discovery is significantly lower priced than Fluent. It is, as you mentioned, an entry-level product. But again, there's a couple of different versions of Discovery based on what the client needs. So I would, again, also recommend just sending a mail to me and Laura with a short description of what you want to do, and we can maybe set up a Teams call to discuss that further.
Hi, Kid.
Hello,
Kid.
is there another question?
Kid, but would it be fair to ask you guys just to give us a ballpark figures? You know, we as a ballpark, someone would know that, I mean, at 5 kilometers away, I cannot afford it, or it's something that I can look into. The reason why I asked the question about affordability, I found that Ansys is very complex, and it's a super software to have. And when I was using it at university, the price that I was being told, I'm looking at, is it something that can be commercially viable for small SME, small, I mean, medium enterprises, consulting engineers like in South Africa or in Africa? We just wanted to have like a ballpark figure. If you can give us, not really like prescriptive figures for a specific client. I don't know if that's a fair question to ask. There's a follow-up on the price.
Again, Eliphas, that is quite difficult because of the different pricing ranges, right? So you've got different packages of the software that include different capabilities. You've got packages that are for startup companies. You've got packages that are for academic companies. So I don't think it's something we can necessarily discuss sensibly here. But again, if you just send us a mail, we don't have to give you, for instance, an exact quote. But as soon as you've discussed with me, Laura, personally, just slightly more what you are aiming for and what your company is, then we can give you a ballpark price specifically for your company. Like I said, it's very difficult to do it here, right? Because then we've mentioned the price, and let's say the situation is different then for different people in the chat. We can't mention one price and then that's only sensible for one or two of the people in here. So that is definitely something we'd rather discuss directly one-on-one with you guys.
And hi, it's Laura here. Eliphas, what I can do, I've got your email address. I will send you some costings after the call, just to give you some idea. But then we need to take it further and give you your bespoke, specific pricing that will work for your company. Okay. Right, I think that is roughly all the questions, unless there's anybody else who still have a question. And as I